What is your name?
Alright, hi, my name's Alyssa.
Okay, and your major?
I'm a physics major and I am minoring in biology and chemistry.
Which university are you come from?
Lamar University.
Lamar University. Okay. How do you feel the last week?
Last week was fun. I learned what neutrinos are.
Okay. And this week, are you excited about the new topics?
Yes,
What do you think?
because so far it's not hard.
Okay, thank you. Hi. What is your name? And your major?
Physics.
Physics. Okay. Which school you come from? UOPH. Okay. And how do you feel last week?
I feel pretty good. Still
Okay.
shocked about everything, but it's a good feeling.
Okay. And this week, are you excited about it?
Yeah. Today's really interesting.
Okay.
And I'm really excited about like the Big Bang stuff and things like that.
Okay. Thank you so much.
Thank you.
What is your name?
Daniel Reyes,
Daniel. Okay. What is your major, Daniel?
physics,
Physics. And where the school you come from?
Carleton State University.
Okay. And how do you feel about last week?
I know what a neutrino is now.
Okay. That's good, at least. And how do you feel this week?
Feels like another language, but
Okay. Yeah, it seems pretty difficult. Okay, that's good. Thank you so much.
Okay, hi, I'm Americano. I'm from UTRGV. I'm a physics major. Last week in NuSTEAM we did neutrinos, and this coming week we're doing Big Bang Theory and nuclear physics.
Okay, nice. Thank you.
Hola,
Hola. What is your name?
my name is Ashur Tariq. I'm a Bachelor's of Science in Engineering and Physics.
Okay. Where school are you come from?
I'm from Lamar University.
Okay. And how do you feel last week?
Last week, it was a lot to cover, but I think I understood most of it.
Yeah?
Particle physics, neutrinos, and stuff.
Okay. And how do you feel now?
Well, I didn't learn anything today yet, so I'm just waiting on the lecture to start.
Okay. Thank you, Asher.
You're welcome.
Hey,
What is your name?
Deshaun,
What is your major?
mechanical engineering and physics,
Okay. And where school are you come from?
Lamar University.
Lamar University. And how did you feel last week?
Last week, I felt pretty overwhelmed with a lot of knowledge.
Okay. Did you catch it?
Yeah.
Okay.
pretty good, I'm getting it.
And how do you feel this week?
This week, same thing. Same thing, but we going strong. Definitely strong.
Okay, thank you.
Dr. Anthony Timmons, a professor at University of Houston. Huge privilege to teach the NuSTEAM class of their second week. What are we learning? We're learning about high energy nuclear physics, how detectors work.
The Big Bang Theory.
The Big Bang Theory.
Uh-huh.
So lots of exciting and stuff. I'm currently my research is at the Large Hadron Collider.
Okay.
I work on the Alice experiment. I'm currently stationed there for a year, but I was very happy to come back and teach a little bit about what we've
Hi guys, I'm here with Dr. Belwit.
Hi, I'm Rene Belwit. I'm a physics professor at the University of Houston, and I'm working in relativistic heavy ion physics, and
Okay.
I'm teaching the class about quark-gluon plasma and how we form it at the big accelerators in Brookhaven and Geneva.
What we're going to learn tomorrow.
Tomorrow we're going to learn about the signatures we found about the quark-gluon plasma and
Okay.
the debris and what we found in the debris of very violent heavy ion interactions in terms of new particles and new features of the quark-gluon plasma.
On behalf of the staff of Brookhaven National Laboratory, welcome. Welcome to our award-winning Scientific Research Center. Operating since 1947, Brookhaven has made world-changing discoveries meriting 7 Nobel Prizes.
Hello people, how are you? Now I can say that we ended up week 2. So for this time, we studied the physics from the beginning of the times. Dr. Timmins explained us the Big Bang, and is the most well-known theory that attempts to explain the origin of the universe and the time itself. So according to this theory, 13.7 billion of years ago, all matter and energy in the universe were condensed into an extremely small and hot point. Due to the quantum fluctuations, an inflationary process began, causing the universe to expand exponentially as it cooled down. Energy began to convert into matter, and the first particles to form were quarks and leptons. However, the universe was still too hot to form atoms, so these particles exist in a very important state of matter called the quark-gluon plasma. That is basically a liquid. So in the first beginning of the universe, it was liquid. As the universe cooled, further hadrons and eventually atoms began to form for 400 million years. The universe exists without visible light. This phase is known as the Dark Age. After this, the first generation of the stars emerged and began producing visible light, and marking the end of the Dark Age. The second generation of the stars followed, forming galaxies and leading to the universe that we can see and we can measure today. So we have a lot of pieces that supports the evidence of this theory. First of all, the universe is expanding. So the farther away an object is, the faster it moves away from us. This observed via redshift means the stretching of the light waves makes the light appear more red. So the second evidence that we have is that the universe is uniformly cold, around 2.7 Kelvin. As the thermal energy converts to kinetic energy, the universe continues to cool down. Then the abundance of helium. 20% of the universe is made of helium, so it could only have been produced during the hot and dense conditions, just 3 minutes after the Big Bang. So the Dr. Timmins also gave us a brief introduction about the standard model of particles and how particles are organized. Now I understand that particles are classified as fermions and bosons. Fermions include leptons and quarks. Hadrons are made of quarks and are divided into baryons. Baryons are 3 quarks, and mesons are conformed by 2 quarks. Bosons, on the other hand, are known as the force carriers. Quarks are very special because they interact with all the fundamental forces. Their interaction via the strength force is due to their color charge, which is something related to electric charge, but it is not the same. Quarks can form hadrons, and interestingly, if you add the mass of the 3 quarks in a proton, it adds up only to 15 MeV, like 5 MeV H of 1. So the actual mass of the proton is about 1 GeV. So where's the other mass? Where is the 985 MeV? So some of the mass is due to the Higgs mechanism, but the most important part of the mass comes from the energy stored in the strong field, binding the quark together, thanks to the E is equal to mc squared. We also discussed how particles interact. They can either collide or can decay in their own. Interestingly, the proton is the only known particle that is completely stable and doesn't decay. So other particles can decay, and we use the Feynman diagrams to describe these interactions. We also saw Feynman diagrams last week, but now we understand how it works and how is the interchange of particles. The interactions between particles are mediated by fields, and each field is associated with a boson. The Heisenberg uncertainty principle tells us what we can know both particles' momentum and position simultaneously. It also implies that we can borrow a lot of energy for a very short time, allowing the creation of a massive particle that can decay very quickly. By using this and setting a particle as to the speed of light, we can estimate the range of each force. So approximately the weak force is around 2 times 10 to the minus 18 meters. These are mediated by the W and Z bosons. The strong force, for example, has both finite and infinite range because the gluons are massless, but you can also measure the range of the pions between the nucleons, and this is 1 times 10 to the negative 15. And also the electromagnetic force that is infinite because photons are massless. So we also learned about the fine structure constant, which describes the strength of the electromagnetic interaction, and its value is approximately 1/137. So another fascinating topic was particles, accelerators, and detectors. I really like this topic. Scientists use them to recreate the high energy condition of the early universe. Particles are accelerated to nearly the speed of light, and then they collide to studying the resulting interactions and the particles form. There are two types of accelerator: the fixed target, where the particle beam hits a stationary target, and the colliders, when two particles' beams are accelerated and may tend to collide. So for accelerated particles, we first need to ionize them, and Dr. Belwitz shared a fun fact. So sometimes you can use a hard dryer and an aluminum foil to remove one electron from a particle. So accelerators also use electromagnetic fields to energize particles. There are two types of accelerators: the DC accelerator that use constant electric field to reach about 1 MeV. For example, the Van de Graaff generator, where negatively charged particles in a vacuum pass through a carbon foil to become positive ions. In the other hand, we have the AC accelerators, the linear accelerator LINAC. We use voltage difference like batteries connected to each other to accelerate the particles in a straight line. Then we have the cyclotrons that are circular accelerator where particles spiral outward under a magnetic field. Then there are the synchrotrons that are like the cyclotrons, but they maintain a constant radius, which changes the magnetic fields. The highest energy machines are the colliders. These are far more effective than the fixed target accelerators. For example, the Large Hadron Collider, the LHC at CERN, is 17 miles in circumference and accelerates particles to 99.999991 of the speed of light. And in the other hand, we have the relativistic heavy ion collider, the LHC in New York, which is the one we are going to visit. It is 2.4 miles around and reaches 99.9995% the speed of light. Physicists often use lead nuclei collisions. Lead is the heaviest stable element. It has 82 protons, and colliding with two nucleus, it creates 1,000 of particles. Then it has an extremely spherical nucleus. And something that I didn't know is that nuclei can shape in other ways. It hasn't to be perfectly circular, but the lead does. And the other reason is because it's an anisotropic flow. It means that the momentum is greater in one direction, forming like a pancake-like shape. The goal here is to recreate the quark-gluon plasma. It exists just after the Big Bang. Plasma is the fourth state of matter where atoms lose their electrons, which then they can flow freely. In a quark-gluon plasma, even protons and neutrons break apart, and quarks flow freely. One of the questions we can have is why we can isolate a single quark to study it. Well, there are so many reasons. First of all, the quark-gluon plasma lasts only 1 times 10 to the minus 23 seconds. It requires temperatures to 150 MeV. It means more than 5 trillion of Fahrenheit. It also means 130,000 times hotter than the sun's core. And the third reason is because quark confinement. The strong force gets stronger with the distance, like a rubber band. When you stretch it, it gets more hard. So you will end up with much energy is needed to separate quarks. So you basically can create another quark instead to complete the whole hadron. At the end of the week, we did several activities using Python programming. We had a mini intro course and create 2 projects, a quadratic equation solver using loops, functions, classes, and also complex real solutions. The second activity we did was a data plotting script using providing datasets that Dr. Portillo gives to us. So this week was hard, so much information to absorb, but Dr. Timmins and Dr. Bellwitt explained everything very, very clearly and answered all my questions. So I hope next week will be just as exciting as this was. Thank you so much for watching this, and I'll see you the next week. Bye!